In the previous module we talked about magnetic forces and its effect on charges and generation of current. Here we continue to discover more about magnetism and look at its magnetic field. We will look into Ampere's law and its application in electromagnetism. Let us look at a moving charge which we know will generate a magnetic field where the direction is determined using the right-hand rule. Examining further the figure, the magnetic field is oriented perpendicular to both velocity and distance between the charge and the test point. The magnetic field rotates around the path of the charge as it moves straight. The magnetic field has a similar property as that of an electric field when talking about point charges. Experiments showed that the magnetic field has the following characteristics. The magnitude is proportional to the absolute value of charge q, the magnitude is inversely proportional to the 1 over r squared, this shows a huge reduction in its strength since it is in r squared. The direction is not along the line from the point source which is different from that of the electric field but it is perpendicular to the plane containing the line of the source and the velocity vector. The formulation that fits all these experimental observations is given by equation 1. The parameter mu0 over 4 pi is a constant where mu0 is equal to the value shown here. Here we see in the equation, when the angle between the velocity and distance r varies with angle 0, gives 0 magnetic field. It is maximum when velocity and distance are perpendicular with each other. Rewriting the magnitude of the magnetic field into a vector form, we consider the directions of the distance r and velocity v. Here the term r hat is the unit vector, thus it will have a magnitude of 1 and it is expressed as equation 2. The function is a cross product given the condition that the magnetic field is perpendicular to both the velocity and distance r. In this case we consider several charges that are contained within a conductor. Then the total magnetic field caused by these moving charges is the vector sum of the fields caused by each charge. This small segment dl will have a charge of dq, so for n number of charges the total charge is given as equation 4. The moving charges in this segment is simplified as dq traveling with velocity v. Note that A here refers to the cross-sectional area of the conducting material. So the magnetic field caused by this small segment is given by equation 5. We simplify the equation since the parameters n, q, and v are current which is given here, then we simplify dB to equation 7 shown here. And in vector form shown in equation 8. The law of Biot and Savart is expressed as the integral of the derivative of the magnetic field due to the small segment dl as shown here in equation 9 and 10. It is used to find the total magnetic field at any point in space due to current of charges in a complete circuit. A current carrying wire exerts a magnetic field at point P. Small positive segment dl or dy of the wire produces a magnetic field of dB. The mark X indicates that the magnetic field points into the direction of the page. Here we use the law of Biot and Savart to determine the magnetic field at point P. Considering the distance r and sin, we see that they are equal to equation 12. Substituting these to equation 10 we have equation 13. Here we need to solve for the integral function. Considering the integral part we have to dissect it. We have chosen the angle theta for simplicity reasons, but you can use phi also. We refer to the right triangle for the relationship between the angles theta and phi. So we let tan theta equal to y over x and write it into equation b. So dy then is given by equation c, which is a secant function. We substitute this to the integral function and we equation d. Note that the 1 plus tangent square function is just secant square shown in equation e. When it is substituted back, we are able to reduce the integral function into the integral of a cosine function, which we know the solution to, which is a sine function as shown in equation f. Substituting back the values of the sine theta, we get that it is equal to equation I, where it was evaluated from -a to +a, which is the length of the wire. Finally, we substitute this back to the magnetic field equation 13 and solve the expression for the magnetic field of a wire exerting a field at point P as shown in equation 14. This is the magnetic field due to a conducting rod. When the length of the rod 2 is very large, that it can be considered as infinitely long, then we can approximate that length between segment and point P is reduced to a, then the magnetic field is given as equation 15. Since x is just our distance, then we can write this to equation 16. Here we compare the orientation of magnetic field and electric field with respect to some distance p. For the wire carrying both magnetic and electric field, the direction of the fields at point P appears perpendicular with each other. As the magnetic field points inward of the page, the electric field points to the left of the page. Looking at the side view exposing the cross-sectional area of the wire, we see the same thing. For the magnetic field, the purple dot indicates the direction of the current which goes out of the page, so the magnetic field rotates counterclockwise in this view. Here we have an example. Shown in the figure are two ends of long straight wires that are parallel to each other and perpendicular to the xy plane. Each wire is carrying a current but in opposite directions. Find the magnetic field at points P1, P2, and P3. Find the expression for the magnetic field at any point on the x-axis to the right of wire 2. Using the right-hand rule, we figure the direction of the magnetic field for each wire. We see that they rotate in the opposite direction. We change its view to side view to better solve the problem. The first wire, its current is moving out of the page as indicated by the purple dot, and its magnetic field is rotating counterclockwise. For the second wire, the direction of current is going into the page as indicated by the purple cross, and its magnetic field is rotating in clockwise direction. The positions are indicated here also. The magnetic field at any point by different sources is simply the sum of these fields. The net magnetic field is given as equation 1. In this case, we expect that the net magnetic field is going downwards because the first wire is closer and it has more push towards the counterclockwise direction, thus greater magnitude in the downward direction. The distance r equals 2d since it is the distance between the wire and point 1. It has a direction of j since it is pointing downward in the y-axis. For wire 2 we have equation c. The distance r equals 4d since it is the distance between the wire and point 1. The direction of j is positive since it is pointing upward in the y-axis. Summing the two fields, we have a net magnetic field at point 1 where it is a negative value, mathematically proving that it is pointed downward as shown in equation D. For point 2, the magnetic fields are both pointing in upward direction with respect to the y-axis. Since they are both equidistant, then they both have the same expression for the magnetic field, and it is given as equation A. Then the net magnetic field at point 2 is given as equation F. For point 3, the direction of the magnetic fields are opposite to each other, same in point 1. For wire 1, where we write it in vector form, we have equation G. The distance r is equal to 3d, since it is the distance between the wire and point 3. It has a direction of j hat positive, since it is pointing upwards in the y-axis. For wire 2, where we write it in vector form, we have equation H. The distance r is equal to d, since it is the distance between the wire and point 3. It has a direction of j hat negative, since it is pointing downwards in the y-axis. The net magnetic field then at point 3 is given as equation I. For the case where we write an expression for the net magnetic field at any point on the x-axis to the right of wire 2, we look at the figure. We let point x be that position on the right side of wire 2, so the distances with respect point x from the perspective of wire 1 is given as equation J. Then the magnetic field due to wire 1 is given as equation K. For the second wire, the distance is given as equation L. The magnetic field due wire 2 is given as equation M. The net magnetic field is then given as equation N. This is the net magnetic field at any point on the x-axis to the right of wire 2. Two conducting parallel wires with currents moving in the same direction. Both exert a force towards each other due to the magnetic field they produce. Let us consider the field generated by one of the conducting wires as shown here. The force due to wire 1 is directed towards wire 1. The direction is done using the right-hand rule for magnetic force direction. The magnitude of the magnetic field produced by wire 1 is shown in equation 16. The force that is experienced by wire 2 due to the magnetic field by 1 is given as equation 17. Its magnitude is given as shown in equation 18. The angle phi here as shown in the figure is 90 degrees, which is the angle between the length L and the magnetic field. Substituting the magnetic field produced by wire 1, we get the force in equation 19. This force is just the same amount of force when it is now with respect to the second wire exerting a field to wire 1. So we can just write a general expression for two wires that are parallel with each other as shown in equation 19. The ratio of the force over the length is known as the force per unit area, and it is given in equation 20. Since the forces are directed towards each other, then for two parallel conductors carrying a current moving in the same direction attract each other. If the currents are in opposition with each other, then they repel each other. A current-carrying conducting wire loop produces a magnetic field, and we find the magnetic field at point P at a distance x as shown in the figure. For curved wires, we apply derivatives by taking a small segment dl of the curved wire. The distance between the small segment dl to point P is given in equation 21. The magnetic field exerted by the segment is pointed upward by some angle. The magnetic field has two components along x and y, but only along x will survive since the y component cancels each other as shown in the figure here. We then identify the angles among the parameters here by applying geometry. The main goal is to determine the angle of the x component of the magnetic field. The x component of the magnetic field is then given in equation 24. Substituting the expression for dB for small segments due to a curved conductor, we get equation 25. Note that we are not dealing with an infinitely long wire, so take this into account when writing the type of magnetic field equation. Here we use the r squared, not r. Substituting the value for the magnetic field to the x component equation, we get equation 26. The cosine function is then given as the ratio of the length a and r, and it is shown in equation 27. Based on the figure, we substitute this back to the x component of the magnetic field and we get equation 28. We integrate this and we get equation 29. Which is simpler since it is just an integral of the length dl, which is the total length of the loop, or simply the arc length. Integrating the segment dl is done and it is evaluated based on the whole length or circumference of the conductor, which is from 0 to 2 pi a. So we get equation 30, which is the magnetic field due to a current carrying conductor exerted to a point P. For multiple loops, the magnetic field is just multiplied by a factor of n, as shown here in equation 31. This shows mathematically that by looping the wire multiple times increases the amount of magnetic field. If we let x equals 0, or at the center of the loop, the magnetic field is given as equation 32. At this position the magnetic field is at maximum, and when we move far from the center the magnetic field decreases in strength. Magnetic dipole moment for single and multiple loops. Recall from the previous module the expression for the magnetic moment, which is given as equation 33, where its direction is perpendicular to the surface of the conducting loop as shown in the figure. The area for this loop is given as equation 34. Substituting this to the scalar form of the magnetic moment, we have equation 35. Incorporating the magnetic moment into the magnetic field expression, we get equation 30. For a single loop it is given as equation 36, and for several loop it is given American Samoa equation 37. Recall in Gauss-Euro trademark S law the function is given in equation 38. Where we can measure the electric field by measuring the amount of charge due to the electric flux it generates through an enclosed Gaussian surface. We also recall the Gauss law for magnetic fields, which is given as equation 39. Comparing the two types of Gauss law, the Gauss law for electric flux relates electric fields and the charge distributions, which allows you to obtain the electric field value. However, the Gauss law for magnetic fields does not relate the relationship between magnetic fields and current distributions, and the magnetic flux at any closed surface is always zero. So we cannot use the Gauss law for magnetic flux to determine the magnetic field produced by a current distribution. Ampere's law is not formulated in terms of the magnetic flux but in terms of the line integral of the magnetic field around a closed path, and it is shown in equation 40. We can think of that instead of a surface Gaussian we think of a line Gaussian, or to be more respective it would be more an Ampere's line. This line forms an enclosure. like for this current carrying wire where the current is directed out of the page as indicated by the purple dot here. The direction of the magnetic field would be counterclockwise using the right-hand rule. The line dl and magnetic field B are in parallel with each other, so Ampere's law can be written as equation 41. We recall that the magnetic field for a wire at a point in the imaginary line is given by equation 16. Then we can write Ampere's equation to equation 42. The magnetic field here is factored out because it does not change along the wire due to the symmetrical shape of the conductor and the choice of imaginary line. Just like the Gaussian surface, it is ideal to choose symmetrical shapes for ease of calculations. Evaluating the expression, we get that the Ampere's law is given as equation 43, where it is a product of the current and a constant here, and it is independent of the radius r. We reverse the direction of the imaginary path, so Ampere's law such that the magnetic field dB and the line dl are anti-parallel, and it is given as equation 44. Calculating this would yield to equation 45. This negative product would make sense if the direction of the current would be going inward. To determine the direction of the integration path, we use the right-hand rule also. Using the right-hand rule, the curl of the fingers follows the direction of the imaginary line or integral path, and the thumb points in the direction of the positive current. The integration path or imaginary line does not need to enclose a conducting material as shown in the figure. Based on the figure, we have 4 paths that are symmetrical, so we create 4 integral terms for the Ampere's law. The direction of the magnetic field is done using the right-hand rule, and it is moving counterclockwise. The magnetic field is again tangent to the curved surfaces here. At each integral line, the magnetic field dB varies. So the first term is the outer curve where the magnetic field and the segment dl are parallel directions, so it does not cancel out. The second term is the vertical line, and the angle between the magnetic field and the segment dl is 90 degrees, so it gives 0. The third term is for the inner curve with radius r2, and the magnetic field and the segment dl are anti-parallel, so it gives a negative value. And finally, the fourth term is the horizontal line, and the angle between the magnetic field and the line segment is 90 degrees, so it gives 0. Manipulating the equation and considering that the Ampere's law eliminates the radius or the size of the line integral does not matter, it gives us equation 46, which is 0. It tells us that for a closed line integral it needs a current passing through it. For an arbitrary shaped integral line distribution, we look at the image here. Inside the line integral is the current carrying wire. Ampere's law is given as equation 47, where the phi is the angle between the length dl and magnetic field B. We rewrite this equation in terms of the position of the wire and the small angle theta using the cosine function. Here we write Ampere's law to equation 48, which is in terms of the distance between the wire and the small segment dl. For this type of wire, the magnetic field is given by equation 16. We substitute the value of the magnetic field to our equation, and we get equation 48, where the distance r cancels out, and we reduce the equation to equation 49. We then evaluate this with respect to the angle for an entire loop. We know that the total angle for a complete rotation is 2 pi. So we use this and evaluate the equation, and we get equation 50. This is the general expression for Ampere's law. Note that if the current is outside of the integral line, then the current parameter would be 0 and remains consistent from our previous calculation. The expression for the Ampere's law does not depend on the shape of the path or on the position of the wire inside it. Now for multiple current carrying loops with different directions we consider the figure here. The magnetic field at any point in the line integral is the sum of the magnetic field produced by each wire. The expression for the Ampere-Euro trademark S law now for this scenario is given as equation 51. The current enclosed is just the algebraic sum of the currents contained inside the loop following the sign convention established earlier. So the current enclosed is given as equation 52. If the currents are equal in magnitude, then it is just equal to 2I. And Ampere's law is given as equation 53 for when three parallel current carrying conductors are contained inside the closed integral loop wire. In this case we have two conducting parallel wires that are equal in magnitude but opposite in the direction of current. Ampere's law gives us equation 54. This does not mean that there is no magnetic field present, but rather there are fields being formed, but the net magnetic field is just zero. We recall the Bohr atomic model, and the magnetic moment was calculated as shown in equation 55. In the atomic level, the nature of the angular momentum L is quantized, and it is in multiples of h over 2 pi, where h is the Planck's constant. We rewrite the magnetic moment equal to equation 57, and this quantity is called the Bohr magneton, and it is equal to the value shown in equation 58. Electrons also produce magnetic fields as they spin around their own axis, and we call them the spin properties, which we discussed in the previous module. We recall, as the electrons move around its orbit, it generates a magnetic field. So we expect that all matter to be magnetic, but this is not what we observe in reality. The reason for this is that there is cancellation of magnetic field effects due to different orientations, such as in the domains where tiny magnets inside an object have different orientation, and the net magnetic field would result in zero. For the atomic model, the pairing of electrons, spin up and spin down, in an orbit matters, and those atoms with paired electrons would. Iron is ferromagnetic, and it has 4 unpaired electrons in the d shell or d orbital. Magnetism is a fundamental property like charge. We mentioned that iron is a ferromagnetic material, and we know that not all materials are as magnetic as iron. Here we start with the materials that are paramagnetic. Paramagnetism are materials that have unpaired electrons that are able to be magnetized in the presence of an external magnetic field. When we talk about electron spins, we are talking about spin magnetic moments of electrons. For a single electron, the spin magnetic moment is given by Bohr magneton, and for multiple spins it is a multiple of the Bohr magneton. When a material with a net magnetic moment is placed in a magnetic field, the field exerts a torque on each magnetic moment. We write an expression for the total torque as shown in equation 59. Imagine that each atom produces a tiny magnetic field like tiny magnetic loops. The sum of these tiny loops will increase the strength or the magnitude of the magnetic field. The magnitude of the tiny magnetic field is proportional to the total magnetic moment of the individual atoms per unit volume of the material, acting like a tiny small loop of current. This ratio is called the magnetization of the material, which is vector quantity, and it is given in equation 60. The magnetic field produced by each atom in the material is given as equation 61. Here the constant mu0 is constant. Here we have a solenoid and wrapping around a paramagnetic material. In the absence of an external magnetic field from the solenoid, the magnetic moment is oriented randomly and therefore no net magnetic dipole moment. When current flows through the solenoid, a magnetic field is produced that reorients the magnetic dipole moment inside the material. Eventually there will be a complete reorientation of the magnetic moment due to the magnetic field present. Cross-sectional view where tiny currents are produced, and we can sum the and imagine it to be one net current flow as shown on the figure. The currents in the rod will produce its own magnetic field. The second magnetic field due to the material adds to the total magnetic field, and it is given as equation 62. Substituting the value for the magnetic field produced by the material, we get that the total magnetic field by a material wrapped by solenoid is given as equation 63. Magnetic permeability of a material indicates how the magnetic field lines can pass through the material. It indicates how much magnetic flux can pass through the material, and this depends on the type of material, temperature, and other factors. It is denoted by the symbol Km, called the relative permeability, which is a dimensionless quantity. Its value typically ranges from 1.00001 to 1.003 at room temperature. We write this as the permeability equation 64. If we compare the magnetic field produced by the solenoid and the paramagnetic rod, we have equation 65. The factor here is called the magnetic susceptibility, and this differs for different materials, and in so magnetic permeability it is given as equation 66. This also tells you that the magnetic susceptibility is a dimensionless quantity. Shown on the table the different magnetic susceptibility of different materials. For paramagnetic materials, the alignment of the magnetic dipoles are weak, so the magnetic susceptibility of these materials are very small. We can say that because the order of the magnetic susceptibility is so small that its effect does not really have that much of a strong impact on the overall magnetic field. Rewriting the total magnetic field with the incorporation of the magnetic susceptibility, we have equation 67. The equation shows that the presence of the paramagnetic material into the solenoid increases the total magnetic field by the is factor, but the magnetic susceptibility is so small that it does not increase it that much. Considering the source of the magnetic field that induces the magnetic field in the paramagnetic material is a solenoid N loops, we can write the net magnetic field as equation 68. Now let us consider just the solenoid and determine the magnetic field produced if it was infinitely long. Here we have an infinitely long wire where the magnetic field is only inside the core. Using Ampere's law to determine the magnetic field produced, we draw the integral line distribution into 4 segments as shown by a rectangular shape here. So we write Ampere's law into equation 69. The integral terms at lines BC and DA have a perpendicular relationship between the magnetic field and the length dl, then it is 0 due to the cosine of 90 degrees. The integral term at line CD, where there is no magnetic field, since the magnetic field is only present inside the core due to its nature of being infinitely long, then it is 0. Then we are left with a term for the segment AB, so we have equation 70. We factor out the magnetic field and evaluate it over the length L. The enclosed current is just equal to the number of wires with current flowing inside the integral line, so we have equation 71. Since we are dealing with an infinitely long solenoid, we replace N over L to the N as the number of coils per length L, as shown here in equation 73. Magnetic field due to an infinitely long solenoid with a paramagnetic core. We incorporate the previous calculation for an infinitely long solenoid magnetic field as shown in equation 73 in finding the total magnetic field for a solenoid with a paramagnetic core inside, and it is shown in equation 74. The magnetic moment inside the paramagnetic material tends to align itself with respect to the presence of magnetic field. This is opposed by random motion inside it, such as thermal activity, which increases the randomness of its magnetic moment orientation. This behavior is described mathematically by Curie's law, which shows a decrease in its magnetization of the material with increasing temperature as shown by equation 75. Named after Pierre Curie, where C is a constant and different for types of paramagnetic materials. Here it shows the inverse relationship of the temperature and magnetization of the material. The ratio of C and T is equal to magnetic susceptibility, and it is given as equation 76. Plotting this equation, we see the relationship of the magnetic susceptibility and temperature, where we see a decrease when there is an increase in temperature. Here we have a demonstration of Curie's law. Here a metal is heated at high temperature and then placed near a magnetic material. While the material is still hot, it is not attracted to the magnet. However, when it begins to cool down, it is then attracted towards the magnet. This shows the effect of temperature on the orientation of the magnetic dipole moments in the material. It increases the disorder, thus preventing it from forming a uniform magnetic field. In some cases there is this modified version of Curie's law, which is the Curie-Weiss law, which describes the magnetic susceptibility of a ferromagnetic material in a paramagnetic region above the Curie point shown by the equation 77. The temperature Tc is the Curie temperature and T is the temperature of the material. Shown on the graph how the Curie-Weiss law is imagined, where we see a point that separates ferromagnetism behavior and paramagnetism, which is at the Curie temperature. Since diamagnetic materials have paired electrons, then there is no dipole moment. Diamagnetic material creates magnetic dipoles due to an external magnetic field. However, the magnetic field produced by these materials are in the opposite direction as the external magnetic field. There is a reversal of the current direction inside the material, and it moves now in counterclockwise. The magnetic field produced by the diamagnetic material is in the opposite direction as the external magnetic field. When following the same calculation as we did, the magnetic susceptibility is a negative value. Table here shows some common diamagnetic material. Pyrolytic carbon is a diamagnetic material. At room temperature it levitates by its repulsion from the strong magnetic field of neodymium magnets. Ferromagnetic materials have domains that have uniform magnetic field, but each domain can have a different orientation. In the presence of an external magnetic field, these domains' magnetic moment will align. Ferromagnetic materials have very high magnetic susceptibility, in the order of 1000 to 100,000. Solenoids with a ferromagnetic coil create a very large total magnetic field, such as iron, which has a magnetic susceptibility around 6000. The presence of a magnetic field alters the size of the domains in favor with the direction of the external magnetic field. We see in the images how it gradually changes with respect to the strength of the magnetic field. Hysteresis is a property of ferromagnetic material where we magnetize and demagnetize the material. At point O, initially the material starts with a randomly oriented magnetic moment. At point A, an external magnetic field is introduced and reaches a saturated magnetization state. This point is also called retentivity, and it is the material's ability to retain a certain amount of magnetic property in the absence of an external magnetic field. This is also the same for point F. At point B, the external magnetic field is cut off, but it retains a magnetization due to the altered domains. At point C, a reverse external magnetic field is introduced that reduces the magnetization to zero. This point is called coercivity. It is a state where an amount of reverse magnetic field is achieved such that the material is completely demagnetized. At point D, the reverse external magnetic field creates a saturated magnetization state in the reverse direction. At point F, a reverse external magnetic field is zero, but magnetization is still present, but in the opposing direction. At point G, the external magnetic field is back to the positive direction and it creates enough magnetic field to reduce the magnetization to zero. Then it goes back to the point where it reaches a saturation of magnetization. There are practical applications of the hysteresis property of ferromagnetic materials such as memory drives like hard drives, magnetic tapes, and credit cards. Here we summarize the three types of magnetism. Diamagnetism is the only one with the negative sign of magnetic susceptibility, which suggests that when it is magnetized it becomes repulsive with respect to the direction of the external magnetic field. The magnetic susceptibility range of the diamagnetism and paramagnetism are very small. Ferromagnetic materials have very large magnetic susceptibility. In terms of dependency of the magnetic susceptibility, ferromagnets are dependent on them. When increasing the temperature, which reduces the magnetic effect by increasing the randomness of the magnetic dipole moment, only the diamagnets are not affected by it. Here we have the different sources of magnetism for the three types of magnetism. Diamagnets are due to electron charge when it is magnetized. For paramagnets, they already have magnetism but it is just randomly oriented. For ferromagnets, they are due to domain-oriented dipole moments. Note, there are also other types of magnetism such as antiferromagnetism, polyparamagnetism, spin glass, cluster glass, metamagnets, and supermagnets, and they have interesting properties also. You can learn more about them in solid-state physics. That is it for now, and I hope you learned something new today. For questions and comments you may send them to diyeslearningstuff@gmail.com. You may review the slide on YouTube at Dies Learning Stuff. Note, please do not forget to use your school email. Also write your complete name and class section. Thank you for listening and see you next module.